Ah, okay, it's going live. Okay, we're live. Let's get started. Professor Dr. Schaefer.
Yeah, thank you very much. I want to thank first the organizers for this very kind invitation and kind introduction. In this introduction, I have to object. I'm not professor yet, but maybe in the future. So today, I want to convince you that condensed matter physics is a fascinating branch of physics in the theoretical and also in the experimental way. And for this, I want to take you to a journey on the dance floor, where I want to say that it takes always two to tango. So we want to discover the physics of correlated electron systems together. And before we do that, I want to point out first my roots, namely in dancing and physics, so to say. So I was born and raised in a small town in Austria called Langenlois, which is famous for its very good wines. And as every 16-year-old Austrian, I was more or less forced to go into dancing school, where I did my first tango steps. Then I went to Vienna, where I did my bachelor and master studies at the Technical University under the supervision of Professor Held and Toschi. And there I learned to dance in a competitive way, and also had the honor and pleasure to go to some balls where Vienna is also famous for that. I then switched to France in my postdoc period as an Erwin Schrödinger fellow with Professor Antoine Georges at Collège de France and École Polytechnique. And also in France you can dance, for example, in the beautiful Palace of Versailles. And now I ended up in Stuttgart, where since September 2020, I'm the leader of an independent Max Planck research group named the Theory of Strongly Correlated Quantum Matter. And also Stuttgart is actually a dance sport hotspot in the world. So you can see my history is a mixture of dancing and physics. And this is also why I structured my talk in such a way. So we will start at the very basic steps, so an orientation, what are electronic correlations, and I will present to you an everyday example of those. And then we will go really into the physics, namely of condensed matter systems with strong correlations. We will learn how to model such complex systems. And then I will present to you two examples, which are very prototypical of such systems, namely first the so-called Mott metal to insulator transition, where you will see a breakdown of band theory. I will introduce to you the so-called dynamical mean field theory, and we will see how to include also non-local correlations there. And a second, even more complex example, namely, I will introduce to you quantum criticality in the context of quantum magnetism, and we will explore the magnetic phase and cone anomalies in the Hubbard model. So we will go from very easy to quite complex at the end. But let us start with an everyday example of electronic correlations. And during the preparation of my talk, I simply Googled Cambridge University and dancing. And what came out is this very nice video, but don't be shocked. It has a very atmospheric and very emotional music in the background. It is a recruitment video of the Cambridge University dance sport team with, very engaged couples and very good couples. And we will take out 3 episodes afterwards of this video and actually relate it to physics and strong correlations. You can already hear it's a bit of a Lord of the Rings theme, so very emotional, very rapping, so to say. Very engaged couples. I like the atmosphere there. I like the spirit. There are also formational themes here. Turning beginners into champions, that's also a nice spirit of Cambridge University, I would say. This guy is also very good. Yeah, now, of course, if the video is now over and you will ask yourself, what has this to do with electronic correlations? Well, let's take 3 episodes out of this video. Namely, the first one, where a solo couple is dancing on the dance floor. And for the description, for the physical description of this one couple on the dance floor, it's quite clear that this couple cannot be correlated. Mathematically speaking, this means that if you have two operators, you take the product and then its expectation value. This expectation value will factorize in the product of two expectation values. So for the description of this one couple, it is just necessary to take into account the movement of one couple. A bit of counterintuitively, this is also true for this formation team, because the movement of one of those couples is determined by the other couples, but in a very, very, let's put it, static way. So also in this situation, the product of the operators will factorize into the expectation value, into the product of these expectation values. But what are we really interested in is this very engaged scene, namely the correlated regime, where for the description of this correlated and very crowded ballroom, you have to really take into account the movement of every of those couples on the dance floor. So this is so to say, an everyday example, but how does this translate now to strongly correlated electron systems in condensed matter? Well, the nice thing about this branch is that out of these correlations, out of, for example, the movement of very many electrons, really fascinating examples of physics can emerge. For example, high temperature superconductors, Mott metal to insulator transitions, or Mott Hubbard insulators, quantum criticality, and also physics in optical lattices. And I will show examples of nearly every of those fascinating phenomena of condensed matter physics. Let us first start with superconductors. And as you probably all know, superconductivity was discovered in 1911 by Heike Kamerlingh-Onnes, who cooled down mercury with liquid helium down to more or less 4 Kelvin. And he observed that the resistivity first, when he cooled down, was dropping quite smoothly, but then it had an abrupt drop at more or less zero resistivity, which he could measure. And this phenomenon is now called superconductors. After this initial experiment, there were initiatives to combine metals into metallic alloys to raise the temperature where this drop of the resistivity happens, which is called the critical temperature. But you see, I mean, this was a period of nearly 60 years here, and not so much happened in the increase. So if you would project, I think, this critical temperature line to the year when this crosses room temperature, I think we would be in the year 2300 or so. However, one came up with empirical rules of how to find new superconducting materials with even higher critical temperatures. And they are summarized in an experimentalist viewpoint, namely the so-called Bernd-Matthias rules. The first one is high symmetry is usually good. So if you want to have a compound which has a high critical temperature, you should at best aim at cubic symmetry of the lattice. The second rule is that high electron density is good. So you want to be actually near a metal. And for example, mercury is metallic. A third rule is stay away from oxygen because it spoils very often metallicity. A fourth rule is stay away from magnetism, so from ordered phases which are not superconducting. And the fifth rule is stay away from insulators. However, the most important rule maybe of this experimentalist viewpoint rules is the sixth one, which is stay away from theorists. But it's quite hard to do so, for example, in our institute here, where we have both experimentalists and theorists at the very same place. These were these Matthias rules, which were empirically found. However, in the year 1986, Bernhardt and Müller did experiments on so-called cuprates, which are copper-based materials, where you have, for example, the crystal structure plotted here. And this crystal structure is built in such a way that you have copper oxide planes. So, for example, the first Matthias rules here is completely spoiled because you have two-dimensional square lattice planes. So you have actually a quite low symmetry in the system. Also, the second rule is not really fulfilled because the parent compound of this so-called cuprates turns out to be a very bad metal, actually. As I said before, this compound is built of copper oxide planes, so also stay away from oxygen did not work. Stay away from magnetism did also not work because the parent compound is an antiferromagnet, as we will see in a minute. And this antiferromagnet is an insulator. The only rule which turned out to be fulfilled is stay away from theorists, actually. So let's take a look at the phase diagram of a prototypical representative of the cuprates, namely this one. So what you see here is a phase diagram as a function of temperature and doping. So you introduce a different material or a different element, and like this you dope the system. What you can see here is that this phase diagram is very, very complex. So you have a superconducting dome, as we saw before, which shows so-called unconventional superconductivity. It shows antiferromagnetism and an antiferromagnet at low doping, which also shows some kind of Mott-Hubbard transition. Actually, it's a charge transfer insulator. However, some properties of those can be modeled as a Mott-Hubbard transition. And just as a brief reminder, an antiferromagnet is simply a magnet with spins pointing in the opposite directions when you change the lattice site. Also, this phase diagram shows a quantum critical point, namely if you quench this antiferromagnetism to T equals to 0 through doping, you get a quantum phase transition at 0 temperature, and I will come to this in the last part of my talk. And there are two strange regimes, which is the so-called pseudo-gap regime and a strange metallic regime with strange resistivity exponents here. So you see this phase diagram is very, very complex, and the question which I have to ask as a theorist is, how can we model such a complex phase diagram? And in condensed matter, we are usually in a quite good position because we know our Hamiltonian, which we want to solve and which we want to treat. And the basic full body Hamiltonian consists, I split it here into two terms. So one term is the term where the electrons do not interact with each other. And this is basically the kinetic energy of the electrons, and maybe also the ions, and the interaction of the electrons with the potential energy of the ions. The second term is the mutual electron-electron interaction. And this is the thing which is really giving the emergent properties of our materials here, and which we are interested in. However, there's a caveat, of course. We know the Hamiltonian, but the problem is that our systems usually in condensed matter consist of more or less 10 to the 23 constituents at minimum. So the problem is, how can we treat quantum mechanically such a large system? And there are in principle two routes to go theoretically. So one is we could search for approximate solutions to this full many-body Hamiltonian. So we keep the full many-body Hamiltonian, but approximately solve it. And there is a very famous strategy to do so, which is called density functional theory, DFT. So not to be confused with DMFT, which I will introduce afterwards for the treatment of strong correlations. You could think of doing perturbation theory like GW and other methods. However, in this talk, we will proceed with a different path, namely to approximate the Hamiltonian directly, but in such a way that we capture the essential physics still of the compounds we want to treat. And one of the most famous approximations of the full many-body Hamiltonian is named after John Hubbard, which is the so-called Hubbard model. And you see, this Hubbard model consists only of two very, very simple terms. The first term enables the electrons to hop from one lattice site to another. So we say hopping, we mean actually tunneling. And the other term is a very crude approximation of the Coulomb interaction. Namely, it only takes place when a site on this Hubbard model is occupied by two electrons, one with spin up and one with spin down. only then we have to pay a Coulomb penalty. Of course, this is a very crude approximation. However, it turns out, as we will see also afterwards, that this Hubbard model can capture many aspects of, for example, the cuprate compounds. The only problem with this model, on the other hand, is that it is not exactly solvable in every dimension and in every regime of the phase diagram. So we have to find ways of describing the properties of this Hubbard model. And we do this, especially in my group, in a numerical fashion. So we think of numerical algorithms, how to calculate properties of this Hubbard model. And these numerical algorithms for finite temperature properties basically fall into 4 classes. So one class is numerically exact techniques, like, for example, lattice quantum Monte Carlo, where you simulate your complete quantum system on a finite sized lattice, and then try to extrapolate to the thermodynamic limit, so make this lattice larger and larger. Then there's so-called diagrammatic Monte Carlo, which aims at a perturbation series of this model, but to very high orders, so that you converge actually in your perturbative series. But as I said before, these numerically exact techniques are not applicable in every regime of the phase diagram. So we also have to do approximations there. And very famous approximations are so-called mean field theory. And this is in contrast to the next one, the aesthetic mean field theory. For example, you encountered this, I guess, in your basic statistical physics courses as the Weiss mean field theory of an Ising model, for example. And then there is a very famous extension of this, which is called dynamical mean field theory, or DMFT. And this I will describe later on. Just to mention it here, the DMFT only takes into account quantum fluctuations, so temporal correlations. But in some situations in physics, we also want to describe non-local, so spatial fluctuations. And there we have to extend the dynamical mean field theory framework to include them. And I will show you 2 examples afterwards of this inclusion of non-local correlations. And there is a 4th category to summarize all other common many-body techniques. For example, functional renormalization groups, so FRG, or tensor network techniques nowadays. So this was a basic introduction into what are correlations, how can we model correlations, how can we describe such model systems numerically. And I will now show you a first example of an effect, which is really a quantum correlation effect par excellence, namely the Mott metal-to-insulator transition. For this, we switch to a different material, namely nickel oxide, whose crystal structure you can see on the right-hand side. For this compound, we can do a so-called band structure calculation. And just as a reminder, what a band structure is in the condensed matter system, you have here a plot of energies, the so-called bands, which are allowed for the electrons having a certain momentum, which is the x-axis here. And what can we learn from such a plot? If we consider zero energy here, which is the so-called Fermi level, which separates the unoccupied states from the occupied ones, we can see that in this band structure calculation, the bands are so to say, going from the region where we have the unoccupied state and to the region where we have occupied states. So they are going through the Fermi level, which means that I can quite easily excite those electrons, namely thermally, to, for example, conduct electricity. So this means, out of the band structure calculation, this nickel oxide should be a metal. This we can also see when plotting the so-called density of states. And the density of states is the projection of this band structure onto this y-axis here. And it tells you how many states you have per energy spacing. And you see again, at the Fermi level, we have, out of the band structure calculation, we have some weights. So both plots tell you that this compound should be a metal. However, the problem is now, if you do really the experiment on this compound, what you see in the density of states is that you get a gap at the Fermi level. So you don't get states but you have a separation at the thermal level, the so-called gap. So the experiment would sees that this compound actually is an insulator. So you can now ask the question, what is actually missing in these band structure calculations? And the point there is, missing is an exact description of electronic correlations, which is stemming from this Hubbard U, so from this Coulomb interaction in our Hubbard Hamiltonian. And this was first discovered actually by a professor of Cambridge, namely Sir Neville Francis Mott. So it's Mott's problem, so to say. And he asked the question, what about now this U actually, so the electronic, the Coulomb interaction, and out of it, the correlations in the system. So can we describe and calculate such an insulator, which we will then call a Mott insulator, in the Hubbard model? And for this, first of all, I want to do a very, very brief excursion to Feynman diagrams. Feynman diagrams are physical, so to say, pictures of physical processes which are used to calculate, for example, transition amplitudes. In the Hubbard model, we have two basic constituents of such Feynman diagrammatics. Namely, first of all, the free propagation of a quasi-particle with momentum k, which is called the free or non-interacting Green function, and the local Coulomb interaction U. Now, with these basic constituents, you can construct so-called one-particle level diagrams, and this is directly connected to experiments. So you shoot one particle into your system, let it propagate and interact with the system, and take it out again, and you calculate, so to say, the transition amplitude of that. And this you could do, for example, in first order, let's say, perturbation theory, where you have one Coulomb interaction here, second order where you have two, and so on. And you can sum these contributions up. And if you sum this up, there is a systematic way of how to do this summation, which is called the Dyson equation. And the Dyson equation now exactly depicts such a one-particle level diagram. Namely, you let the particle freely propagate into your system, let it interact once, twice, and so on. And this you can sum up in a geometric series, where the kernel of this interaction, so to say, is a so-called self-energy sigma. So just very illustratively, this self-energy sigma encapsulates all the correlation effects with respect to the non-interacting system. So all the one-particle level correlations are encapsulated in this object. More you don't have to know about Feynman diagrams in this talk. Now, with this knowledge, we can go back to our methods, how to treat the Hubbard model. And we start first with a mean field theory, which is, as I said before, quite analogously to the Ising-Weiss mean field theory of the Ising model. What you do is, you take your many-body Hamiltonian, so your Hubbard model in this case, and you create a mean field in space. So you take out one atom and average over all the other sides. And what comes out is, in the static mean field theory, that you get a self-energy, so to say, which is purely static, which is a number. So it's not frequency, not momentum dependent, or not time dependent, or real space dependent. The nice thing in the Ising model, for example, is that this solution is actually exact in the limit of so-called infinite dimensions, which is not a futuristic concept, but simply means that you have many neighbors of your sites. And in this limit, this mean field theory becomes exact. What we can now do is we can extend this concept to the so-called dynamical mean field theory. So you again take your many-body Hamiltonian, you take out one atom, you average over all the lattice sites. But now you retain the fluctuations in time, which means that on your atom, you can either have zero occupation, so no electron sitting, one electron, either with spin up or with spin down sitting, or two electrons sitting. And this can change in time. And like this, your self-energy becomes a function of time or a function of frequency. So your dynamics is, so to say, still in your description included. However, the DMFT does not include spatial correlations, so correlations in space. We will come to that later on. Also here in the DMFT, this mapping is exact in infinite dimensions in this case. So the DMFT is actually the exact solution of the Hubbard model in infinite dimensions. So with this short presentation of the methods, we can now come to our original problem, namely the problem of how we get an insulator, although our band structure is not predicting an insulator. And for this, we can go to a very, very simple embodiment of the Hubbard model, namely the single band Hubbard model on a two-dimensional square lattice. So you only have a single band in this case. We can now calculate the phase diagram of this model. I now disregard any magnetism by means of the dynamical mean field theory. And you have the temperature axis here, and here the local Coulomb interaction as the x-axis. Now you can see that we get here a region of the phase diagram shaded in blue, where we get a so-called first order phase transition between a metal at weak coupling, so at low U, and you can see this via plotting the density of states here again, and you have weight at the Fermi level. And on the right-hand side of a so-called Mott insulator. And now you see that we didn't change the band structure of this model. We still have, so to say, in the non-interacting limit, we still have one band, but now all of a sudden, with a high U value, we get two bands, namely a so-called lower Hubbard band and an upper Hubbard band. These two bands are split, and we don't have weight at the Fermi level. So we have an insulator. However, this insulator does not stem out of the crystal structure, so out of band theory, but because the Coulomb interaction is so large that not two electrons want to sit on the same lattice side anymore. So like this, you can think of, you can never conduct, because for conducting an electron in a half-field system, where you have an average occupation of one electron per lattice site, you always have to create a double occupation of your lattice sites. And this is now forbidden, so you have a gap. If we go to intermediate couplings, we get features of both. So we get a so-called quasi-particle peak here in the middle, and the onset of these two Hubbard subbands. This quasi-particle peak vanishes at this transition, and the Hubbard the subbands really split into two. Let me just briefly mention that this Mott Hubbard metal to insulator transition is very closely related also to its universality class to a very common phase transition, which all of you know, namely to the liquid gas transition in water. We can now flip this phase diagram here, and what you see is that you have this first order phase transition line also in this phase diagram of the water, and you even have a critical endpoint here. This you also have in the Mott metal to insulator transition described by DMFT. Above this critical endpoint, actually you cannot distinguish anymore really between, here in our case, between a metal and an insulator. It's just a gradual process, which we call a crossover in this case. So let's go back now actually to our original problem, namely nickel oxide. So can we now describe this compound by our dynamical mean field theory? And the answer is yes. We can do a combination between band structure calculations. So for example, DFT, density functional theory, and DMFT, which is called LDA plus DMFT. So we have included the crystal structure, while the band structure, plus the Hubbard interaction. And you see now that if we compare this LDA plus DMFT spectrum, which includes the correlations, with the experimental data, we almost lie on top. So in this case, what is really making the difference is the correlation physics, so the Hubbard U. We can now ask ourselves, okay, I've told you before, DMFT, dynamical mean field theory, neglects spatial correlations. The question is now, what happens to the Mott metal to insulator transition if we now include spatial correlations, which are in some physical situations very crucial? Well, for this, we have to extend our dynamical mean field theory framework to include those. And there are in principle two routes to go. So one are cluster extensions of DMFT. I've told you before, for DMFT, we take one atom out of our many-body Hamiltonian and average over the other lattice sites. Here we take out a cluster of interacting atoms and average over the rest. And like this, you can include spatial correlations, but only up to the cluster size, of course. And these methods come in several fashions. I will not go into detail about this. I will show you an example afterwards of CDMFT, where we have a real space cluster. However, in some situations, for example, approaching second-order phase transitions, we also want to include long-range correlations. And this can be done by so-called diagrammatic extensions of DMFT, which rely on Feynman diagrammatics and on the extraction of higher order correlation functions. I will not go into much detail about this here, but they also come in various flavors, and we will see an example now of those two classes. So let's go back to our single-band Hubbard model calculation and see what the inclusion of spatial correlation does to it. Well, if we include short-range spatial correlations by means of this cellular dynamical mean field theory, we see two things happen. So this is now a finite size cluster of 2 by 2 lattice sites. First of all, the critical onset of the Mott-Hubbard transition is significantly reduced. So this means you need less Coulomb interaction in order to get an insulating state. Also, the coexistence region shrinks, and the shape of this curve is reversed. What happens now if we include long-range correlations here? And for this, I come back to this phase diagram of water. What we get if we include long-range correlations is that the transition vanishes in favor for a Mott-Hubbard crossover. So a gradual crossover from a metallic to an insulating phase. And please also note that now, regardless of the value of the Coulomb interaction, we always get an insulating state at low enough temperatures. And you can ask the question now, of course, why is this the case? Well, this has to do with the ground state of the model, which we can calculate in mean field theory or even in D gamma A, so in our diagrammatic extension of DMFT. The ground state of this model is an antiferromagnetic insulator. If we go to finite temperatures, the so-called Merman-Wagner theorem prohibits that this order is extended to finite temperatures. However, there are significant fluctuations, namely magnetic fluctuations, still present at finite temperatures. And how can we, so to say, how can we quantify this? Well, we, for example, can zoom into this so-called weak coupling regime of the phase diagram and calculate the spin-spin response function. In this case, the spin-spin response function is showing an antiferromagnetic behavior because the sign of this function is changing from lattice side to lattice side if I would make a cut. This is the first thing which we see. The second thing is that at temperatures above this crossover line, we have a so-called correlation length, which is this damping factor of this curve, of 4 lattice sites, which is not super large. On the other hand, if we go lower in temperature, below this crossover line, we see that these fluctuations get quite severe, and the correlation length is about 1,000 lattice sites. And this, so to say, these extended fluctuations, they are enforcing the electrons to localize. So this is why we get an insulating phase at weak coupling. These our D gamma A calculations have been confirmed later on by numerically exact diagrammatic Monte Carlo calculations of Fedor-Szynkowicz et al. So this was an introduction to one of this of the phenomena in correlation physics, which is the Mott metal to insulator transition. Now I want to switch a bit of the topics and go to the topic of quantum criticality and give you a short introduction to this. So again, we will start at classical phase transition, and one of those examples you have already seen, namely the liquid to gas transition, which is a first order transition with a second order critical endpoint, and it shows a discontinuity in the density. However, afterwards, we want to describe magnetic phase transitions. So I want to give you an introduction to that. One example you for sure know all, namely the paramagnetic to ferromagnetic transition. So if you have, at home a ferromagnet and you heat it up, you will see that at some point it loses its ferromagnetism and gets a paramagnet. And microscopically speaking, this results in going from this ordered pattern of spins ordered in one direction at the ferromagnet to this randomly pointing spins at high temperatures. How can we describe this now physically? Well, the ordered phase is first of all indicated by the finiteness of an order parameter. And in our case, we simply sum up all the spins, also taking into account their orientation. And this means in the ordered phase, we get the finite value for this total magnetization. As the spins are randomly ordered or randomly positioned in the randomly orientated in the paramagnetic phase, there will be a zero order parameter there. However, already in the paramagnetic phase, we can see that approaching this second order phase transition, we will get a growth in the susceptibility in this compound. In this case, the so-called ferromagnetic susceptibility. And this is just the derivative of the total magnetization with respect to an external magnetic field. In momentum space, this would correspond to the spin-spin susceptibility at Q equals to 0, 0, 0 in 3 dimensions. This quantity at the phase transition will diverge. We can now do this very same description at the paramagnetic to antiferromagnetic phase transition. And an antiferromagnet, I told you before, is when you have local moments which are pointing in opposite directions when you change the lattice size. For this, of course, the previous order parameter, so the magnetization, would be 0 also in the ordered phase. However, we can introduce another order parameter, which is called staggered magnetization, which has a phase factor in there, which copes with the orientation of the spin, so that it gets finite in the ordered phase, but still is still 0 in the paramagnetic phase. And this we can also do for the susceptibility, which is now the so-called antiferromagnetic susceptibility here, which is the derivative of the staggered magnetization with respect to the staggered magnetic external field. This in momentum space corresponds to the spin-spin susceptibility with Q equals to pi pi pi, and this quantity here at the phase transition also diverges. Going a bit into a generic system, we have here the temperature and some non-thermal control parameter, for example, the density, as we will encounter afterwards. I told you before that in the unordered or thermally disordered phase, the order parameter, here denoted by phi, is equals to 0, whereas in the ordered phase, it requires a finite value. In the disordered phase, however, also the susceptibility has a finite value and it grows approaching the phase transition. Now, what I want to point out is that in the vicinity of the phase transition, we have a regime which is called classically critical. And the exciting thing about this classically critical regime is that also for different models, there are some properties of these different models which are universal. For example, critical exponents. So for models which fall into the so-called same universality class, and this is usually determined by, for example, the symmetry properties of the order parameter, they can be totally different, but have the same values of those critical exponents. And two prototypical examples of these critical exponents are shown here, namely the one of the temperature dependence of the, for example, magnetic susceptibility, and this is usually denoted by gamma, and another one, namely the one of the temperature dependence of the correlation length, which is usually denoted by this exponent nu. Also, what I want to point out is that if you go close to this classical phase transition, you can always assign an energy scale. In this case, it's a thermal energy scale, which is simply given by Boltzmann K times T. And you can assign even a quantum energy scale, which looks a bit complicated. So it's the so-called reduced temperature to the power of the correlation length critical exponent and dynamical critical exponent. The details do not matter. What you can see here is that when going close to the classical phase transition, the thermal energy scale always wins above the quantum energy scale, which means that at finite temperature, being close to a classical critical regime, we will not encounter quantum effects. However, if we quench the transition to T equals to 0, we get a true quantum phase transition, going from an ordered to a quantum disordered state. Now you could argue that, of course, this is a purely academic discussion, because as an experimentalist, I cannot go to 0 temperature. However, the sheer existence of such a quantum phase transition and a quantum critical point, which this one is called, is not purely academic, because it also influences the whole excitation spectrum of the system at finite temperatures. And one very nice experiment of this, which shows that, is an experiment on a so-called heavy Feynman compound, where they measured the electrical resistivity and drew this phase diagram where they shaded the regions where the temperature dependence of the electrical resistivity is T squared in blue. So the T squared is the usual Fermi liquid behavior, which you would expect from the resistivity of a Fermi liquid, whereas the red shaded region indicates the so-called strange metallic phase, which is described by a linear T dependence of the resistivity. So you see that this existence of a quantum critical point also shows up at finite temperatures. Now the question is, coming back to our methods and to our beloved Hubbard model, can this phase transition also show up there? And can we describe this? And we will show that it's indeed possible. So we go now from the two-dimensional system to the three-dimensional system, and we now take into account the magnetism of the model. Again, you have the temperature axis here and the interaction axis. And in DMFT, you indeed get this separation line of a paramagnetic and an antiferromagnetic phase, which is called the nail temperature. How did we calculate this? Well, in DMFT, we also can calculate susceptibilities, not only spectral properties. In this case, the antiferromagnetic susceptibility, which I introduced before. And where this quantity diverges coming from above, there we have the phase transition. If we now include non-local correlations again, by means of the dynamical vertex approximation d gamma A, we see that this nail temperature drops a bit. And this is due to the fact that these non-local correlations destroy the order in this intermediate regime. We now go into the classical critical regime. Namely, we take a look at the regime close to the phase transition. And we now plot the inverse of this antiferromagnetic susceptibility as a function of temperature. In DMFT, you see, of course, at the nail temperature, this quantity diverges, which means that the inverse will go to 0. And you see that this quantity is a straight line. And this is actually, in 3 dimensions, a mean field result. This is not correct, because we would expect in 3 dimensions that the Hubbard model, at least at very high interactions, would fall in the same universality class as the Heisenberg model, which does not have this linear behavior. If we now include spatial correlations, however, on top of DMFT, by means of this d gamma A, we see that we get an alteration of this critical exponent from the DMFT value of 1 to the d gamma A value of 1.4, which falls into the same regime as the 3D Heisenberg model. And this was later on confirmed also by other techniques. Now we go one step further, and we dope the system. So we introduce holes into the system. What happens then? So in DMFT, we see that the nail temperature as a function of this hole doping drops, and we also eventually get down to zero temperature. Again, we calculated this phase transition line by calculating the magnetic susceptibility and its divergence. If we now include on top again spatial correlations, this nail temperature drops a bit. And what is also interesting is that we don't get a pure antiferromagnetic phase transition anymore throughout the whole phase diagram. But at low doping, we get indeed still this antiferromagnetic phase, but at larger doping, we get the so-called incommensurate phase, which you can view as a spin spiral, so to say, so spiraling from one lattice side to another. What we also get is we get here a quench of the transition to t equals to 0. So we want to analyze now the quantum critical point there. There we can think of what do we expect for the quantum critical exponents at this quantum critical point. Well, before I showed you that the DMFT as a mean field theory shows this critical exponent of 1 for the susceptibility. It would show for the correlation length a critical exponent of mu 0.5. The 3D Heisenberg model shows a bit of an alteration of this, namely a gamma of 1.4 and a mu of 0.7. For the quantum critical exponent from weak coupling theory, which is the so-called Hertz-Millis-Maria theory, and that's a quantum extension of the Landau-Ginzburg-Wilson framework, we would predict for this universality class a mu of 0.75 and a gamma of 1.5, which is not too different from the Heisenberg exponent. So what do we now get numerically? So we start again at half filling, where we have the classical phase transition, and now I plot the inverse correlation length here as a function of temperature. Also, the correlation length at the phase transition diverges, so the inverse goes to 0 here, and we can extract the critical exponent. It's 0.72 in this case, which is not too far away from the 3D Heisenberg value. This stays also true for larger doping, going to this incommensurate phase at low temperatures. However, if we go to the quantum phase transition, we see that if we extract now this critical exponent, also within our numerical error bars, we get an exponent of 0.91 plus minus 0.1, which is not in the Hertz-Millis-Maria universality class. So what is going on here? Well, we took now pen and paper again and went a step back, namely, we analyzed the so-called Fermi surface of this object. And the Fermi surface again separates the unoccupied from the occupied region of let's say, my band structure. And what you see here is, this is the Fermi surface now in 3 dimensions. We have certain pairs of lines in this Fermi surface, which are lines of so-called cone points. And these cone points have the property that they connect large parts of the Fermi surface by a momentum vector q and having opposite Fermi velocities. So what does this now has as an influence on our critical properties? Well, the details of the calculation I want to spare to you. We did a mean field calculation there, where we introduced also the cone lines at final temperature. And what the outcome was that the critical exponents of the QCP actually changed. Namely, they changed quite dramatically from mu 0.75 to mu 1 and gamma 1.5 to 0.5. And this is quite unexpected because we are at quite strong coupling, so we have a high U. So you wouldn't expect that the band structure is really much important for the critical exponent at the strong coupling. The second thing, which is quite surprising, is also that the order of this universal exponent changed, namely the usual Fisher relation, which states that 2 nu should be equals to gamma is strongly violated. Actually, it is reversed in this case. Let's go back to our numerics and let's check whether this could be true for our quantum critical point here. So you would have these critical exponents with the error bars. This is the Hertzmiller-Moria, which is not fulfilled. However, the cone QCP seems to be fulfilled. As I said, it's quite surprising having this at strong count. So this was a bit of a more involved example of strong correlations. And with this, I'm actually also at the end of my talk. So I showed you that strong correlations can lead to fascinating examples of physics, ranging from high temperature superconductivity, unconventional superconductivity, the Mott metal to insulator transition, to quantum magnetism. I introduced to you the dynamical mean field theory, which is the working and power horse in our group, which was the first framework which could explain the Mott-Hubbard metal to insulator transition in a consistent way. I also showed you that we can include non-local correlations on top of the MFT, which can lead to quite severe changes in the phase diagram of the Hubbard model, be it at the Mott metal to insulator transition or at the magnetic one, displaying their quantum criticality, which has a certain twist to it, namely that cone anomalies on the Fermi surface alter the critical exponents and therefore change the universality class of the system. So with this, I want to acknowledge and thank very much my group members. So Marcel Klett, my postdoc, Mario Malcolms de Oliveira and Michael Meixner, my PhD students, Patrick Czeppe, who was an internship student and will join as a bachelor, and my secretary, Jeanette Schüler-Knapp. Also, I want to thank enormously my many collaborators, of which I show only a certain selection here, for being part of this amazing journey over the years. And of course, you for your attention and again for this very nice invitation to the talk. Thank you very much.
Right, thank you very much. I think I'm going to turn off the live stream now so that people are more comfortable asking questions. So let me end the stream. Okay.